Welcome to AP Podcast 6.2. This is on enthalpy, and enthalpy is abbreviated as H. Oops. And enthalpy is simply known as the heat content of a substance. Now, when we did specific heat stuff last year, when we were finding the Q value, we were doing energy problems in a similar manner to what we're doing here. And this stuff is a little confusing, but if you look at this equation they've given us, here's enthalpy, and it equals energy, and that's internal energy, plus the pressure times the volume. And you might remember from a couple lectures ago that we had this energy equals Q plus the work involved. And if you recall, work was involved by calculating the pressure times the change in volume, right? So it's kind of all related. So if we think about the change in enthalpy, it really equals the change in internal energy plus the pressure times the volume change. Now, as a special condition, and a condition that we usually see in AP, if you are at a constant pressure, which again most of our problems are going to be, it turns out that the Q equals H. So we're going to kind of use them interchangeably, and how to get that is a little beyond the scope of this course, but if you really want to look at how they do it, it's a pretty simple derivation. It's on page 248 of your textbook. So think of H and Q as essentially the same things. I'm sure there's some professors or some teachers out there that would want to lynch me for saying that, but for our purposes, it's going to be essentially the same thing. So the change in enthalpy is simply the energy flow as heat. And at a constant pressure, if you think about a constant pressure, whenever we do an experiment in our classroom, we've got a beaker or some kind of flask, and the pressure doesn't change. So this pertains to us all the time. So a couple terms you're going to see quite a bit is you're going to see heat of reaction. And all that is the amount of energy that is involved, whether it's being given off or absorbed, during the reaction. So you'll see heat of reaction, and you'll see change of enthalpy. And for our purposes, they mean exactly the same thing. So keep that in mind when you see those two phrases, because hopefully you won't get confused. Now, if we want to find the change in H, just like anything else, it's going to be like a starting point and a final point. But for us, it's going to be the products minus the reactants. And I'll show you how to calculate that in just a little while. So let's look at a couple of these problems, because they're not too bad. They're pretty straightforward. But we've got an example here. So we've got some methane. We've got 1 mole of it. And it's burned at a constant pressure. Again, constant pressure is important for us. That makes all these equations and math a lot easier. And notice 890 kilojoules of energy is released. Now, why in the world is that important? Released. Well, if it's released, that means it's an exothermic reaction, right? And so, for our purposes, when we get a value in joules, we want to make sure that we put that negative sign, because remember, exothermic means energy is given off, and from the system standpoint, that means that it's negative. So let's just go ahead and calculate this out. I've got 5.8 grams of methane, 5.8 grams. Now, what do I do with grams, as you guys well know? Well, we find some moles. So 1 mole of methane weighs 16.0 grams, and that equals 0.36 moles. All right? 36 moles. Now, let's look at the information they gave us up here. It turns out that every 1 mole gives off 890 kilojoules. So really, for our purposes, that's a conversion factor. So we're going to go ahead and make sure our units cancel. For every 1 mole, we have 890 kilojoules. And if you want to put a negative sign right here, because it's given off just to remind yourself that it should be negative, then that's fine, or you can do it at the end, either way. But when you work that out, you get a negative 320 kilojoules of energy. All right? So there's the first problem. Not too bad, right? We just got to pay attention to how much energy is either absorbed or released, and of course the moles. So let's try another problem. Here we have a reaction where we're taking some hydrogen gas and some oxygen gas, and we're making water. Students in my class last year did this reaction a couple times, and the demo, the bottomless jug, was all about this one. So let's look at this. Now we've got these coefficients in front of the problem, which we did not have in our last problem. So what this really means is that a negative 572 kilojoules of energy, I should just say 572 kilojoules of energy, is released for every time 2 moles of water react, or 1 mole of oxygen, or 2 moles of hydrogen. We've got to keep that in mind when doing these problems so we work it out correctly. Now look at the amount of starting materials we have. So again, we're just going to do the kind of problems we've been doing all this time. And so I've got 2.56 grams of hydrogen gas, and 1 mole of that weighs 2.016 grams. Okay. Now, instead of equaling out, I'm just going to keep going. Now look at our coefficients. For every 2 moles of hydrogen gas, 572 kilojoules will be produced. So I'm going to put 2 moles down here. And this is a common mistake. Students will often put 1, but you've got to look at the reaction to get the right value. So for every 2 moles, I get 572 kilojoules. And I guess we ought to keep the sign there, right? Because we want to make sure we get the right value. And so when I work that out, I get a negative 726 kilojoules. Okay? So there you go. That's how much heat is evolved. Not too bad, right? Well, let's look at a couple other scenarios and see what we would have. So pause the video for a second. Try and do number 31, A through D, and see if you get the same exact answers that I get. All right, let's see how you did. Are the following processes exothermic or endothermic? Solid KBr is dissolved in water, and the solution gets colder. Well, there's your clue, right? The solution gets colder, so this is an endothermic reaction, right? Natural gases burn. Well, there's the key right there. Burned, so that's exo, right? When a concentrated solution of sulfuric acid is added to water, the solution gets very hot. Again, exo. And water is boiled in a tea kettle. Ooh. Did you get the right answer? This is an endothermic reaction. Okay? Now, a lot of students put exo because they go, oh, boiling, we're heating it up. But you got to remember, what is the system doing? In order for water to boil, it's got to absorb energy. And it's absorbing the energy from the stove. So if it absorbs energy, endothermic, right? Okay. Let's move on to the next thing, calorimetry. Now, we did a lot of this last year. Actually, we didn't do a lot of it, but we did some of this last year. And this was simply measuring the amount of heat transferred. If you recall, we heated up some metal, we dumped it into a cup, we measured the temperature change, and we calculated the heat. All right? There's a new term here that we did not get last year, and that is the molar heat capacity. First of all, specific heat capacity, not a problem for you, right? And if you remember the unit, you've got joules per gram degrees Celsius, or if we were using the Kelvin scale, joules per gram Kelvin. But molar heat capacity, there it is, molar. You can imagine maybe that it's not grams, right? It's moles. So instead of joules per gram degrees Celsius, that's joules per mole. So it just really saves you a step. But I don't want you to get tripped up by that word, molar heat capacity. Because if they give us moles, we can use the molar heat capacity. If they give us grams, we can use a specific heat capacity. Not too tough. All right, let's look at a problem here. Or actually, I'm sorry, here's some more terms. And again, I'm just going to skip over this. If you want to pause the video and write this down, you can. But this is all a review of last year. The important part of this whole slide is, of course, this equation right here. And if you remember, we're talking about heat of reaction. Well, for our purposes, that's Q, right? Because delta H equals Q. And if you remember from last year, Q equals S, being specific heat capacity, times the mass times the change in temperature. So let's do a problem and pause the video. I'm going to work this out and show you my answer, and then we'll go from there. All right, did you get that answer? Now, one thing I wanted to mention is in the previous slide, if you look at it over here, there was an S right there. You see that S? Oops, let me get that out of the way. See that S? And your book has S for specific heat. Last year we used C, so hopefully that didn't confuse you. I use C here because I'm used to using C from our regular chem book. But when I work this out, I get 2.88 times 10 to the negative 6 joule, or 10 to the 6 joules, which is a ton of energy if you think about it, right? Way bigger than we're used to. But look at how much stuff we're trying to heat up. 75 kilograms, that's a lot of stuff. Okay. So anyways, hopefully you got that answer. If not, we'll look at it tomorrow. We can go over it. And then there's one last little thing I want to show you, because every once in a while they'll refer to a bomb calorimeter when doing calorie problems. And this is kind of a cool thing. In college, some friends and I did a lab, and then after the lab, we put a little piece of Snickers in there, or we put a piece of cookie in there, and just for fun tried to see how much energy he was giving off. But this is, imagine this is your styrofoam cup calorimeter on steroids. And basically what they do is they put a sample in there, they pump this bomb right here full of pure oxygen gas at a very high pressure, and notice that the volume doesn't change, right? So if the volume doesn't change, the pressure times the volume changes Z, or 0, and then the energy equals the Q. So you can get the value there. And then what you have inside here is you have some water with a little spinner that stirs the water. And just like we do with a coffee cup, we have a thermometer right here that measures the temperature. And so you can stick anything in there. And what's really neat in this dish when you take it out is there's nothing hardly at all, because it just gets vaporized. And so this is kind of how, this is what real chemists use to find the calorie content of foods and stuff that you see on your packages. So there you have it, enthalpy, pretty interesting stuff. The problems aren't too difficult. The concept's a little odd at times, trying to relate it to the internal energy and the work and all that. But for our purposes in AP, it's not too bad. So